Okay. Okay, just quickly again. We have the rules of exponents. A to the B times A to the C is A to the B plus C. We can illustrate that and maybe get a convincing example if we do 2/3 times 2 to the fourth. 2 to 2/3, 2 to the third times 2 to the fourth. 2 to the thirds, 2 times 2 times 2, 2 to the fourth, you got 4 2s. Well, that is, you remove the parentheses by commutative and associative laws and so forth, then you get the string of 7 2s. So what you got is 2 to the 7th, which is 2 to the 3 plus 4. And of course, that equals 2 to the 7th. A to the B raised to the C power looks a lot like this. And you think, people will want to multiply the B and the C here, but it's obvious that that doesn't work. If we multiply the B and the C, we're going to get 2 to the 12th. So that doesn't work. Down here, it looks like we ought to raise B to the C power just because of the way it's written, but we don't. We do what it says. And if we do what it says, we do A to the B raised to the C power, we get A to the B times C. To illustrate that, then you'll see a more extensive explanation in the open math videos and in the text. But 4 squared raised to the third power means 4 squared times 4 squared times 4 squared. And 4 squared is 4 times 4, so we got 3 groups, each with 2 4s in it, which gives us a total of 6 4s, and of course we can write it out that way. And that gives us 4 to the 6th, and that's 4 to the 2 times 3, because we have 3 groups of 2 4s. So that's how the raising a number to a power and raising that to a power, okay? A power of a power, an exponent of an exponent, okay? You can always test these laws if you ever get confused, and I used to. I used to test them all the time because I know what it looked like and I wanted to do what it looked like. But I knew that I couldn't always do what it looked like. So I just think, okay, 2 squared times 2 cubed, oh, yeah, multiply it, okay? And I did that for a good little while, even after I got pretty secure with the laws, because I always wanted to go back to what they mean. So that after a while, I just pretty much never screwed that up, okay? Screwed it up plenty of times early, but I always managed to catch it and correct it, almost always. Okay, so anyhow, okay, back to this pattern now. We have a pattern, 2 to the third is 8, 2 squared is 4, 2 to the first is 2, and we know that. Because of course, 2 to the first is 2, 2 to the second is 2 times 2, so we multiply this by 2. And 2 to the third is 2 times 2 squared, which gives us 8. Going the other way, we cut these numbers in half, okay? We go from 8 to 4, well, we got 8 by multiplying 4 by 2, okay? So we're going to get 4 by dividing 8 by 2. So we divide 8 by 2 and we get 4. We divide 4 by 2, we get 2. We divide 2 by 1 and we get 2 to the 0, which is 1. And people want to say 2 to the 0 is 0. In pre-calculus class, the majority will think the 2 to the 0 is 0 for some reason I can't fathom. I actually get through algebra courses not knowing that 2 to the 0 is 1 and not remembering it. Well, the reason is that everything's done with a calculator. Nobody ever does calculations. Well, that's a terrible exaggeration. Okay, they do, but not enough. Not enough to remember these basic facts, and not enough to make sense out of these rules either. Okay. Anyhow, 2 to the negative 1 then is what? Well, if you follow this pattern, the exponents go 3, 2, 1, 0. You can go on negative 1, negative 2, negative 3. All the negative exponents. But every time you've got to divide by 2 if the pattern's going to make any sense. So 2 to the negative 1 has to be 1 divided by 2. Okay. 1/2. 2 to the negative 2 is half of that. Well, half of 1/2 is 1/4. 2 to the negative 2. 2 to the negative 3 is 1/8. Not very carefully, but you know, this is half of a half, this is half of a fourth. This is half of 8, half of 4, half of 2, half of 1, etc. Okay. Well, another way to write 2 to the negative third is 1/2 to the third, right? Okay. So this is 1/2 squared. This is 1/2 to the third. So we can continue the pattern. And those dotted lines, let's actually continue the pattern. 2 to the negative fourth is 1/2 to the fourth. That's half of 1/2 to the third. If we do 1/2 times 1/2 to the third, we get 1/2 times 2 to the third, and that's 1/2 to the fourth. So our rule is two to the negative n is 1/2 to the n. And we can generalize for any number a to the negative n is 1/a to the n. Okay. Okay. So let's see if you can apply that to some of the expressions on the sheet. Okay, so we asked what's the first thing you want to do here, and the natural answer is, well, use a distributive law. Well, you certainly could, but you got a denominator here. You can multiply both sides by 3, and that denominator is going to go away. And so you say, okay, well, I do 3 times z equals 3 multiplied by 7/3 times 2k plus p. Okay, well, I've got a fraction here. I'm going to write that as a 3/1. So 3 times 7. Well, we're not going to do that. I can multiply. I can rewrite this as 3 times 7 over 3 times 1 times 2k plus p. Okay. And the mistake I've seen from some is people want to multiply this by 3 as well. Now you only got to multiply by 3 once on this side. If there are a bunch of terms that need to be multiplied by 3, yeah, you do that. But in multiplying 3 times 7/3, it just gives you 7, and you know that. Okay. And multiplying 3 times 7/3, you've multiplied that side by 3. Okay, so you get 3z equals, well, 3/3 is 1, so that's 7. times 2k plus p, and you're done. Now let me just make a point. Why you just multiply the 3 by the 7/3. If you multiply 3 times 2 times 8, that equals, well, it's 3 times 2 times 8, which is 48. Three times 2 times 8 is not 3 times 2 times 3 times 8. Multiplication doesn't distribute over multiplication. Okay. I mean, you know this is right with the numbers. Okay. And you know this is wrong because, of course, you get 6 times 24, which is 144. Okay. You know 48 is right for this calculation. You know 144 is wrong. Okay. It's the same thing here. You multiply 3 by a product. You multiply 3 by something times something. You multiply that 3 by this something, or multiply that 3 by this something if you wanted to. But you can't do both. So we want to keep that in mind. But again, now what we see is if you multiply both sides by 3, this is what you get. And no one skips steps. Okay. If you don't skip steps, you're probably going to be less likely to make a mistake of this nature. And other mistakes. So we at least want to write this down. And once we see this, yeah, maybe we skip to this step. We might not have to write this one out. But we want to make sure we think this. We want to make sure we understand why we get 7 instead of just getting it out of habit. Because there are a lot of places our habits are going to mislead us. Okay, so question, sketch a graph of y equals x plus 3, just kind of approach it, we are with graphing. And we see that, well, if you make a table of y versus x, let x have values 0, 1, 2, 3, 4, 5, whatever. Then if you plug the value of x in here, if x is 0, you're going to get 0 plus 3, y is going to be 3. If x is 1, y is going to be 1 plus 3, which is 4. If x is 2, y is going to be 2 plus 3, which is 5, and so forth. So we're going to get these values, which gives these points in the graph. The graph's going to look like this, okay? Now we want to know for what value of x do we get y equals 0? And we can get that by solving a simple equation, or we can just look at it and see. Okay, for what x is y equal to 0, and just looking at it, you can say, well, x would have to be -3. The only thing you can add to 3 to get 0 is -3. Okay. So we answer that question. Well, x is -3. If x is -3 and y is 0, doesn't that tell us at this point should be -3, 0? Now, if you extend the scale of the graph that you drew, you can mark off units, okay? If your x units are like so, you mark off 3x units and you're going to get that point. Okay, verify that. Just go ahead and mark your graph and see how close that comes. Okay, so that's a convincing argument. Everybody made their scale here and came out pretty close to -3. Okay, now I asked what is y when x equals 0? The answer to that question is, well, if x is 0, 0 plus 3 is 3, so y is going to be 3. And that gives us this point here, which is 3, 0. Those are the only 2 points we need to graph this thing. We don't need 5 or 6 points because this is a linear function. It's just got a, no x squared, no x cubed, nothing fancy, no x's in the denominator, just y equals x plus 3. So we call this the point where y equals 0, call that the x-intercept. Okay, has to occur on the x-axis because that's where y equals 0. You're above or below the x-axis, y is 0. And what's y when x equals 0? That's the other question we ask, and we get a point. Okay. So I ask you to do the same thing. Answer the same questions for y equals 2x plus 7. And then put that information on a graph. So find the distributive law, we can multiply this by this and we get all this. Okay, and that means we just multiply x by this and minus 3 by this, x times x plus 4 minus 3 times x plus 4. And then we just do this, x times x is x squared, x times 4 is 4x, negative 3x here, negative 12 here. Collect that all together, we get x squared plus x minus 12. Now, just taking off on this, we also did this multiplication where we got a much bigger thing. We multiplied these two together the same way we did this. Then we had to multiply this by all this. Took a few steps, but we got this other thing. Then we asked the same questions. What values of x makes x minus 3 times x plus 4 equal to 0? Okay. Well, you can see that if x is 3, x minus 3 is going to be 0. That's going to make it 0. X is 4, x at negative 4, x plus 4 is going to be negative 4 plus 4. That's going to be 0. That's going to make the whole thing 0. That means that the graph of this is going to have y equals 0 when x equals negative 4 and when x equals 3. Those are called the zeros of the function. And then we ask, what's the value of this if x equals 0? Well, x equals 0, we plug it in, we get negative 3 times 4, which is negative 12. Well, if x is 0 and y is negative 12, that's this point. Okay, so we have these points and we get something very much like a parabola. Okay. Now, the first attempt usually makes this a low point. That's not really where it should be. Really where it should be is on a vertical line halfway between negative 4 and 3, because a parabola is symmetric. Okay, this will be what we call our axis of symmetry. So that the low point is actually going to occur on that axis of symmetry, and the graph is going to look a whole lot like what we just did. And it didn't do that very well, but that's going to shift the low point over to the left a little bit. Okay, now, if we want to graph this, there would be 3 values of x that make it 0. So we could say, okay, for this function, we have negative 4, negative 2, and 3. And then if x is 0, we get 2 times 4 times negative 3, which is negative 24. But just by asking the same questions, we just answered for a straight line function, we get this. Okay. Another thing we can say is, well, if x is a really big positive number, all these are positive, so they're multiplying 3 big positive numbers. if I multiply three big positive numbers, I get a really big number here. So when I get out past x equals 3 here, the graph is going to go way up. And if x is a big negative number, then all these are big negative numbers. If I multiply three big negative numbers, I get a huge negative number. Three negatives make a negative. Three big numbers multiply to give us a really, really big number. So our graph goes down like this. And now something's all messed up because when I multiply these, never mind. Okay, I can draw a curve that satisfies all this. A curve up through here, down through here, up through here, and on up. And that's what the graph looks like. So again, that's the power of just asking the question, what's y when x equals 0? What's x when y equals 0? It gives us a lot of information about functions like this. We call this a polynomial. This is actually a polynomial too. If we multiply all these out, we get like x cubed plus 3x squared minus 10x minus 24. Now, if I ask you, where's this 0? And you don't know this, well, you better be able to factor that and find this. Okay. In the real world, that really doesn't matter much. Because in the real world, you never get anything in factors. Okay. But you got to learn factoring anyway. So usually when I do polynomials, I stick to the factored form. Makes it easy to answer the questions. What's y when x equals 0? What's x when y equals 0? Okay. And then you're off to the races. If you understand this and this, which I just explained in 30 seconds, and it takes a little more than that. Okay. You got to play around with it some, but that's where this is happening. And that's into some pretty good intermediate algebra there.